Alright, first thing I'm going to do in this section is recommend that you go to Canvas and you click on the very first link in the module, which I just uploaded, which is Common Squares and Cubes. So to show you what it looks like in Canvas, basically on my laptop, we're in this last section where we're doing radicals and the quadratic formula. The very first link is a file that says Common Squares and Cubes. Ideally, you'd be able to print this out. Worst case, just have it as an open window on your computer. This is what it looks like, and I'm going to be referring to this when I go over the problems in this section and the next section. So when I have a problem, like the square root of 12, my goal here is to break this into a perfect square and another number. So what I need to do is go up my list of perfect squares until I find one that divides evenly into 12. So on my list, I have the number, the square, then the cube. I'm going to go to the square column. In the square column, I'm going to go down till I see something bigger than 12. Bigger than 12 is 16 in this case. So 16 is not going to work. I try 9. When I do 12 divided by 9, it does not give me a whole number. So I go to the next one on the list, 12 divided by 4. 12 divided by 4 gives me 3, so I can split this in to two things being multiplied, one of which is a perfect square, one of which is 9. Once I split something like this, I take the root of the perfect square, the root of 4 is 2, and leave the rest of it behind in the root. Looking at the process for number 2, we start with 90, so I go to my list of perfect squares. 100 is bigger than it, so I won't try that. I try 81. 90 divided by 81 doesn't go in evenly, so I try 64. Doesn't go in evenly. I try 49. I try 36. 90 divided by 36, still not even. 25 doesn't work. 16 doesn't work. Finally, I get to 9, which does work. I see that this can be broken into 9 times 10. So I break it into those two roots. The square root of 9 is the perfect square, 3 squared. So I'm left with 3 root 10. If you see a perfect square that goes in right away, you absolutely don't need to use this process where you're dividing by every number to get to it. I'm just trying to show the best way to do it if you're really confused on how I'm reducing these. So when I get to 242, in my list, that's going to take me all the way down to 144, 12 squared. This is the most that I can have to do, having to put in 11 numbers if I can't find one that works. So I start by doing 242 divided by 144. Does not work. Then I do 242 divided by 121. It does work. 242 and 121 can be broken into 121 times 2. So if I put 242 in my calculator divided by 121, I get that yes, I get a whole number, so this perfect square does divide into 242. By starting with the largest numbers, I'm not going to get a case where I accidentally pull out too small a number where I could have pulled out something bigger. For instance, if 6 is really a root, 3 and 2 will both work. So if you work the list from bottom to top, you'll make sure you get the largest one. In this case, the root of 121 becomes 11, and the root of 2 gets left behind. When we go to try 48, 49 is too big, so I start with 36. 36 doesn't work. Try 25, 25 doesn't work. Try 16, 16 does work. This turns into the root of 16 times the root of 3. If I'm using my paper, in the column squares where I see 16, I can look back to number right to the left of it, and it tells me 4, which really tells me the root of 16 is 4. So you can also use the paper that way, where whatever square you have lines up with the number to the left of it. When I go to do 108, 121 is too big, so I start with 100. Doesn't divide evenly. I try 81. Doesn't divide evenly. I try 64. Doesn't divide evenly. I try 49. Doesn't divide evenly. I try 36, and it does divide evenly. This gives me 3 when I divide it by 36, so I can break it into 36 times 3. The root of 36 is 6, which comes out and leaves behind the root of 3. 180, I can try 144, doesn't work, 121 doesn't work, 100 doesn't work, 81 doesn't work, 64 doesn't work, 49 doesn't work, 36 I believe does work. 36 goes into it 5 times, so it breaks into the root of 36, the root of 5. This becomes perfect square, comes out as 6, root of 5 is left behind. We're now getting into ones that have variables. So if you remember in our higher order roots, we did have to deal with these that had a remainder in the variable. When we just did square roots, we didn't. So it's kind of combining those two ideas. Basically, there's an understood 2 under this root. So this becomes x to the 11 halves. That can split into the whole, x to the 10 halves, and then still have left over 1 half. 10 divided by 2 is 5, so it comes outside as x to the 5th. Left under the square root is this number on top, x to the 1st, or I could just write it as x. Here in number 8, 9 is a perfect square, so the root of 9 just becomes 3. Then I get x to the 21 over 2. 3 stays there, I can break this to x to the 20 over 2, and x to the 1 over 2. 20 over 2 is 10, so 3x to the 10th is outside. There's 1 left over under the square root. When I go to number 9, I see that root 50 isn't on my perfect square list. So this is putting both concepts together. I have to start by saying what's the largest perfect square that goes into 50 the way I did in the first 6 problems. So I try 49, doesn't work. I try 36, doesn't work. I try 25 and it does work. Specifically, it tells me that it's root 25 times root of 2. This x is really x to the 3 over 2 power. So I can split this into root 25, that is a perfect square, x to the 2 over 2, that is a perfect square, and then root 2, x to the 1 half left over. This root 25 comes out as a 5. This x to the 2 over 2 is just x to the 1st. Then underneath the root sign, we have this 2 and this x to the 1st. Make sure in the end that anything that came outside the root is being multiplied in front, and anything that stayed inside the root is being multiplied under the root.